Okay, so Unit 3 is the longest unit, or biggest unit, in Science 10. Right? We covered a great deal of material in this unit, starting with like scalars and vectors, and then moving all the way to conservation of energy at the end. Okay, we talked about, well, actually right at the beginning, we talked about types of energy, so it kind of came full circle because we talked about all the different kinds of energy and things, and then at the end we were talking about conserving those kinds of energy. Okay, and in the middle we talked graphing and vectors and scalars, acceleration, work energy theorem, okay, all of that kind of stuff. So the nature of this unit exam will be more like the chemistry unit exam was, okay? Rather than having to memorize a lot of stuff like you did for biology, you have to be able to demonstrate your skills. Okay? So this is a much more skill-based, show me what you can do type of test, as opposed to show me what you know type of test. Okay? There's still obviously a little bit of show me what you know, mostly in the multiple choice. The written response is almost entirely problem solving. Okay, so you'd have, you know, an acceleration problem like was on your worksheet, or a law of conservation of energy problem like we've been working on for the last week or so. Okay, work energy theorem problems, graphing, okay, stuff like that. All stuff that we've done. Most of it we've had labs on as well, and I'm not going to ask you to do anything different on the test than I've asked you to do in either a lab or a worksheet. Okay, so the good news is there's nothing on this test you haven't done many, many times already. Okay, the key here is to review those skills and make sure that you can perform them next week on the test. Okay? All right, if you got questions as we go, please ask. Okay? So, first thing we went over, types and forms of energy. Okay, that was day one. We talked about mechanical energy, chemical energy, nuclear energy, all of that kind of stuff. Okay, that's going to be tested almost entirely, well, actually entirely in the multiple choice. Okay, so I might give you a question that goes something like this. What type of energy would water in a river have? Okay, and the options would be A, chemical energy, B, mechanical energy, C, nuclear energy, D, solar energy. Okay, well, water in a river is moving, and it's moving downhill, so mechanical would be our best answer because it would have mostly kinetic and some potential energy as well. Okay, so mechanical would be our best answer for that one. Okay, obviously it doesn't have nuclear energy. We're not going to be, you know, performing anything like that. Okay, no chemical energy. You can't burn water, right? Stuff like that. Does that sort of make sense? That's kind of how I'd be asking that. Okay. Then we've got systems. Okay, so we talked about three types of systems: open systems, closed systems, and isolated systems. Right? Quick review. An open system can exchange matter and energy with its surroundings. Okay, so right now we are an open system, each and every one of us, because we're exchanging matter, gases, okay, whatever, okay, and energy. Okay, we're hotter than the surroundings, so energy naturally goes from us to the surroundings. We're an open system. A closed system exchanges energy but not matter. Right, so that would be anything that can be sealed airtight. Okay, it can still exchange energy, okay, but it can't exchange any matter. So an example of that would be if you went out and bought a bunch of food at the grocery store and you were going to freeze some of it, you put it in a Ziploc bag. Okay, so that Ziploc bag seals it airtight. Nothing's getting in or out of the bag matter-wise, but as soon as you put it in the freezer, the energy starts leaving the food, and that's how it freezes. Okay, so that would be a closed system. Isolated systems don't essentially exist. Okay? You can never perfectly isolate something so that it never exchanges energy. Okay? There's always going to be an exchange of energy according to the second law of thermodynamics. Right? So it's essentially impossible to create a perfectly isolated system. We can get pretty close, okay? But you're never going to perfectly isolate something by preventing either its loss of energy or its absorption of energy. There's always going to be some of that. Okay? So an isolated system theoretically would exchange neither energy nor matter. Okay, and then we talked about thermodynamics, okay, that's like heat engines, heat pumps, okay, we talked about how your refrigerator works, okay, how it uses energy and goes against the second law of thermodynamics, pumping heat out into the hotter area. We talked about jet engines, okay, how they're a heat engine, they harness the flow of energy from hot to cold to produce mechanical energy, okay, things like that. Right. Again, that's going to be all multiple choice kind of stuff. And we talked just briefly about perpetual motion machines. Okay, you could be required to understand why a perpetual motion machine can't exist based on the first and second law of thermodynamics. Okay, so quick review. A perpetual motion machine is any device that could run indefinitely. Okay, it would require no input energy, it would simply run. Okay. What was the downside to a perpetual motion machine? What can it never do?
Work.
Yeah, it can never do work. Because work is a transfer of energy, and if there's no energy going in, there can't be energy going out. Because then it would be creating energy, and that goes against the first law of thermodynamics. Okay, see where I'm going with this, kind of your explanation on the test. Okay, and the second law of thermodynamics says that energy always flows from hot to cold, okay, or high to low, so energy's always got to flow away from a high energy object, which a perpetual motion machine would be. All right, questions on that energy and thermodynamics part? Okay, so like I said, that's going to be almost entirely multiple choice. The perpetual motion machine part could be written response. You might have to explain that, or it might be a multiple choice question that would require you some understanding of it for it to work. Okay, then we talked about scalar and vector quantities. A vector quantity has two things. What are they? Direction. Right, those are examples of scalar quantities. Speed and time are scalar quantities. They have magnitude, how big they are, and direction. Okay, time and speed and distance. Okay, were the three important scalar quantities we went over. Energy and work are also scalar. Okay, they don't have direction. Okay, energy is your ability to do work, and work is a transfer of energy. They don't have direction. They're simply a number of joules. All right, our vector quantities that we went over were velocity, displacement, and acceleration. Okay, those are all vector quantities. Okay, force is also a vector quantity, but it's not something we ever had to worry about in this unit. And you won't have to worry about whether it has direction or not on your unit exam either. When we started talking about scalar and vector quantities, that's when we went over V equals d over t. Okay, so speed equals distance over time if we're talking about the scalar quantities. Velocity equals displacement over time if we're talking about the vector quantities. Okay, those were fairly straightforward, simple problems. And you will likely be asked about them in the multiple choice. I'm not going to burn a 4 or 5 mark written response question for a V equals d over t problem. Okay? That is beneath you. Okay? It's really worth just 1 mark in a multiple choice type question. Okay, so those were our 2 formulas. Okay, V equals d over t. So V without the arrow, speed, d without the arrow, distance, t without the arrow. Okay, time, well, it never has an arrow. Okay, V with the arrow over top, velocity. Okay, displacement, time. And we have to remember that this can also be calculated this way. Okay, so final position minus initial position over time, okay, can calculate velocity as well, because displacement is calculated as the change in position, okay, or final position, okay, minus initial position. That's how we get that. Okay. Then we went on from there to graphing, okay, and the reason we did that was because we actually used this formula, okay, and this formula a little bit on graphs, okay, when we were starting to interpret graphs that weren't just one straight line, okay, we were able to use V equals d over t to calculate things from a position versus time graph and some from a velocity versus time graph, right? So they could be important there, okay, but no, it would only be on a graph that had multiple sections and not one linear line. So here's something to think about. On the test, for the graphing questions in the written response, graphing questions plural, okay, one of each, one velocity versus time, one position versus time. I'm going to tell you how I want you to solve the graphing questions, okay? What I mean by that is I'm going to tell you whether I want you to use y equals mx plus b or whether I want you to do this. Okay, I will tell you that in the question, and here's how I will do it. I will give you a graph, and if the graph has an equation given on it, so it has y equals whatever written right on it, I want you to use the equation, and it'll say in the question, using the graph and its equation, probably in bold-faced, italicized, underlined font, okay, that means do it this way, okay, because I will have set it up so that if you don't do it this way, you'll get the wrong answer, okay? I realize that this is just a manipulation of this, but if I make the y-intercept anything other than 0, and you do it this way, it won't work, okay? So just be aware, I'll tell you if I want you to use y equals mx plus b or no, okay? Everybody with me there? Just be on the lookout for that. Okay, so for graphing, okay? You were asked to do a number of different things in the graphing part of this unit. One of the things you were asked to do was interpret a graph. And you will be asked to do that in the multiple choice. Okay, so I give you a picture of a graph and I ask you, using the position versus time graph below, describe the motion of the object in section A. Okay, you have to look at it and go, oh, okay, well, what's going on? Okay, so let's say that this is a position versus time graph, okay, and this is section A and this is section B, okay? If that's a position versus time graph, what's going on in section A? Nothing. Yeah, absolutely nothing is going on because the position at the beginning of section A and the position at the end of section A are the same. In other words, the object didn't go anywhere during section A. Everybody follow? If it asks you what's going on during section B, what's it doing there? Okay, declining. That's what the line's doing. What's the object? Moving. Moving which way? Backwards, right? If we start here, let's say this is a position of +5, and we end down here at a position of -8, okay? We were moving backwards, but even more than that. I would be expecting a little bit more detail than that. Moving backwards at, yes, okay, or constant velocity, okay? Because it's a straight line. Okay, it's telling me that the position is changing by the same amount every second, which implies a constant velocity. So these are the kind of things we need to be able to interpret from a graph. okay? If it's a position versus time graph in the written response, and obviously this would not have an equation on it because it's two different sections, okay, then I might also ask you, what's the total displacement of the object? Okay, if I ask you that, then you're going to go, right, displacement is position final minus position initial, -8 minus 5 is -13 meters. Right? So a simple calculation like that, but it's something I could ask you to do on the test. Okay? Similarly, I could ask you, if this whole trip takes 10 seconds, what's the average velocity? And then you go, well, I just figured out this. It was -13. -13 over 10 is -1.3 meters per second using z equals d over t. Okay? So those are the kinds of things you could be asked to do with this type of graph. Okay? This type of graph would not have the y equals mx plus b on it. All right, what if instead of a position versus time graph, this is a velocity versus time graph? Now what's the object doing in section A? So now this graph is showing me how fast the object is going. And here, it's going 5 meters per second. Here, it's also going 5 meters per second. What was it doing during section A? Traveling at a constant velocity of 5 meters per second forwards, or positive 5 meters per second. That's all we can say. Right? What's it doing in part B? Right? It's accelerating backwards. Okay? The entire time its velocity is changing, and we define acceleration as a change in velocity. Okay? I can see the velocity is changing, so accelerating in a negative direction. That would be all I'd be looking for. Okay? On a question like that. All right. If it was in the written response, I might ask you to calculate some things. I might ask you to calculate the acceleration during part A. How many marks would that be out of? What's the acceleration in part A? 0. We just said that it's traveling at a constant velocity in part A. Acceleration is a change in velocity. Velocity is not changing. Okay? That requires no work, no calculation. Okay? It's worth 1 mark. Spoiler alert, watch out for that. Okay? You would be surprised how often I ask exactly that, and I see people do 5 or 6 marks worth of incorrect work to prove something wrong. Okay? People look at that and they're like, oh, okay, what's the acceleration? Okay, how do I calculate acceleration? And they start doing all kinds of math, when all they had to do was look at the graph and go, the velocity didn't change, so it's not accelerating, and be done. Okay? I've seen people spend as long as 10 or 12 minutes on that 1 mark question. Okay? Always look at your point values. If something is out of 1 mark, it requires no calculation. Okay? The answer is right in front of you. Yeah? All right. I could also ask you, what's the acceleration in part B? Okay, well then you would go, all right, well, acceleration equals Vf minus Vi over t. We know the acceleration formula, right? So we'd have -8 minus 5 over 10, and we'd get 1.3 meters per second squared. It just happens I'm using the same graph, we get the same numbers. Okay? Everybody all right with that? Actually, sorry, it wouldn't be 10 seconds because this would only be from 5 to 10 seconds, so it would be over 5. So 13 over 5, whatever that is, 2.6. Okay. All right. Everybody all right with that? Okay, last thing I might ask you to do with a velocity versus time graph. Calculate the displacement of the object. Right? That's where you gotta go. All right, I'm gonna use d equals v times t and go base times height. Okay, I've got a triangle here. That's gonna be base times height over 2, because that's gonna take the average velocity by time. Same for this, base times height over 2. Add them together, get my total displacement. That's where the lockdown happened, right after that. Okay, we went into lockdown after I taught you how to do that. Okay, so it was the last thing we learned in person. Okay, questions on the graphing stack. Okay, there's going to be one of each type in your written response. One position versus time, one velocity versus time. Okay, make sure you look over your 2 labs. I'm going to ask you to do exactly the same thing I asked you to do in those labs. Now, in those labs, the graph we had, okay, the graph we had in those labs looked like this, okay? And you'd get your equation. Okay, if I give you a graph that looks like that, then I'm going to ask you to do what you did on your labs, which would be, if it's a position versus time graph, for 1 mark, I might ask you what the velocity is. What's the velocity? Riley, what's the velocity? It's 1.5. Okay, how do we know that? Okay, this is my equation for the line. On the y-axis is position. On the x-axis is time. So if I manipulate for this number, what I'm doing is going y minus b over x equals m. Well, y is my final position, b is my initial position, x is time. That's the formula for velocity. Okay, those are just little things we have to be able to do, okay, when we encounter a question like this, because it would only be out of 1 mark, because it actually doesn't require you to do anything. The answer's right in front of you. Now, another thing I might ask you to do, calculate the position of the object after 10 seconds. Right, substitute 10 for x. Okay, you're solving for a position which is on the y-axis, so you're solving for a y value. 10 seconds, seconds is on the x, 10 seconds, so 15 plus 2.5 is 17.5 meters. Similarly, I might ask you how long it takes to reach a position of 100 meters. Okay, now I'm giving you y and asking you to solve for x. Okay, all things I asked you to do in the analysis parts of your labs. Okay, so have a look over those and make sure you know how to do that. Okay, questions on that? Okay, there's quite a few marks on graphing on your test. Okay, so that would be one of the things I would review thoroughly. All right, then we talked about acceleration. Okay, A equals VF minus VI over T. You're going to have a problem or two, okay, in the written response about acceleration, so make sure you can do problem solving to do with acceleration. Okay, there might be the odd multiple choice question asking you about acceleration as well, what it is and stuff like that. Okay, then we went into work energy theorem, which we probably spent more time on than anything else in the unit except graphing. Okay, so it's a big concept. Force times distance equals change in energy. You will have 2 work energy theorem problems on your unit exam. One dealing with a change in potential energy and one dealing with a change in kinetic energy. How do we tell the difference? Right, one will involve a change in height, the other will involve a change in speed. If it involves a change in height, then we are talking about potential energy. If it involves a change in speed, then we're talking about a change in kinetic energy. Right, so we look at that within the question and we identify this is going to be a work as a change in potential energy question. Write down our givens. Okay, then we set work equal to we set work equal to the change in energy, and then we go force times distance equals that, okay, and we go from there, right? So force times distance equals the change in energy. It's either going to be kinetic or potential, okay, and off you go. We did tons of examples and then the stuff we've been working on here for the last little while, conservation of mechanical energy, EI equals EF. Okay, the context for those questions, sleds going down hills, roller coasters, jumping out of planes or off cliffs or whatever. Okay, any place where work is not involved. Right? What I find happens to a lot of people on the unit exam with these two types of questions is they get them confused. Okay? They try and solve the work energy theorem questions as a conservation of energy question and vice versa. How do we tell the difference between a work energy theorem question and a conservation of energy question? Garrett?
Work energy theorem question usually have force in it, and conservation of energy gives you a initial velocity, initial height, usually either a final height or a final velocity.
Right. Okay. Work energy theorem problems are going to involve forces. You never get forces in a conservation of energy problem. That's the first way to tell them apart. Okay. The second way to tell them apart is you never have a work energy theorem question that involves both height and speed. It will involve one or the other. Okay. Conservation of energy questions always involve both. Okay. If the height and the speed are changing, it's not a work energy theorem question because I told you you never have a work energy theorem question where both potential and kinetic energy change. Okay? So that's the other way you can tell them apart. The rest of the time, it's context. Okay? Work energy theorem questions usually involve things like bows and arrows, catapults, slingshots, pushing something really hard with something else, okay? Something like that. Whereas conservation of energy questions usually just involve letting gravity do its thing. Okay, something gets dropped, something goes down a hill, okay? Something like that, right? Those are going to be your conservation of energy questions. Okay, so when we set up a conservation of energy questions, EI equals EF, then we expand it out to this, and that's the point where we have to figure out, does it have all four kinds? Are there any of those that I can cancel out? Okay, once we've done that, then we manipulate it for the part that we're looking for. Okay, so if we know we're looking for the final height, that's part of the final potential. So I'd move the final kinetic over here, then I'd put my formulas in, okay, and then I'd isolate for final height. And I say we've done tons of those. They're all the same. Okay, that's the good news about it. You do this again in physics 20, it's all the same. Okay, it never gets to be any different. All right, and then we have efficiency. Okay, so efficiency, basically you just need to understand how it works. There could possibly be a very simple problem in the written response, or sorry, in the multiple choice. Okay, but the formula is on the front of the test. Okay, so remember that efficiency is work out by work in divided by work in, or energy out by energy in. Okay, so you got 20 multiple choice questions, okay? And as we were saying through the review here, those are gonna cover your understanding of different concepts, okay? So, what work is, what energy is, types of energy, thermodynamics, first and second law, okay, things like that. Scalar and vector quantities, knowing the difference. Simple calculations like calculating displacement, final position minus initial position, that can end up in the multiple choice. Simple V equals D over T calculations. There's some graphs, but they are fairly straightforward things. They're not difficult calculations or interpretation type questions. Okay. And then a couple of things about work and energy, okay, in the multiple choice. Again, not calculations, just understanding, okay, situational stuff. Right, in your written response, question number 1, position versus time graph. And I ask you to calculate 3 different things, okay? And that whole thing I told you about the bold-faced, italicized, underlined writing, did that question, okay? Using the graph and its equation, okay? So make sure you use the equation that goes along with that graph. Okay, then you have an acceleration problem. Then you have a velocity versus time graph problem where I ask you to calculate 3 things. Questions 4 and 5 are your work energy theorem questions. Question 6 is a law of conservation of energy question. And the last question is another acceleration problem. Okay, whole test is out of 65. So there's 20 multiple choice, and then there's 45 marks in the written in 7 questions. 16 of the 45 marks in the written are graphing. Twelve of them are work energy theorem. Conservation of energy question is 8 marks. Okay, so think about this. 36 of 45 marks are on 3 concepts. Graphing, work energy theorem, and conservation of energy. What should you focus on?
Those 3.
Yeah, those 3. They're kind of big. All right, questions from you guys? Anything you want me to explain in a little more detail or go over? I believe that, I'm just double checking here guys, but I think the unit exam review is actually the last couple of pages of the units worksheet booklets. Okay, I will post right now then in Google Classroom the unit exam review package, okay, and you can start having a look at that. should see in the stream now in Google Classroom a PDF that is Physics Lesson 23, Unit 3 Exam Review. And I will post the recording I've been making here as well, and so you can watch or listen to that again if you need to. Guys, the rest of class is for doing review. Hopefully some questions come up, because I'd really like to answer some questions if you have them. Okay, that's where we're headed. Noah, you had a question?
I just thought you asked if there's anything we wanted to go over, but,
Yes. Is there anything you'd like to go over?
just like more questions.
Okay. Let's make one up real quick here. I never know how to spell my G. Is it with a G or a J? It never looks right. A slingshot. How about that? Then I know how to spell it. Slingshot. Okay, give that one a try. We'll walk through it in a minute. Good work energy theorem example. So, first thing we want to do is identify what type of energy is changing here. Okay, we've got this slingshot drawn back, and it's telling us that it launches the rock from rest to a speed of 24 meters per second. Speed has to do with kinetic energy, so this is a work energy theorem problem involving a change in kinetic energy. All right, my givens are distance, 0.53 meters, all right, mass, 0.240 kilograms, VI, 0, and VF, 24 meters per second. Okay, so force times distance equals 1/2, actually, sorry, we'll write it, do the whole thing here. Okay, equals EK final minus EK initial. Since the rock is initially at rest, how much kinetic energy does it have initially? 0. Okay, so there's no sense in subtracting 0 or writing that even, we can just get rid of it. So force times distance equals 1/2 mvf squared. I have m, I have vf, I have d, I'm looking for the force. So I'll isolate the force by dividing both sides by d, okay, and then plugging in my numbers. 1/2 times 0.24 times 24 squared, okay, divided by 0.53 meters. All right, so a force of 130 newtons. Okay, actually 1.3 times 10 to the 2 newtons would be the force we would use there. Okay, so there's an example of work energy theorem. All right, we got 3 minutes left. I got to spray down your desk. So if you can clean them off, I will come around.